Okay, let's begin. So I found this very interesting quote. I did not know that Einstein wrote about socialism, but he has written a book called Why Socialism. And I will read a paragraph from it, just some few lines. The abstract concept of society means to the individual human being the sum total of his direct and indirect relations to his contemporaries and to all the people of earlier generations. So this particular quote also sums up the idea of a category, yeah, that the individual is in fact the sum total of the interactions, the external behavior. Yeah, so I just wanted to note that. There are other interesting quotes also if you want to have a look. Okay, so we have started with category theory. Over here we defined the notion of a category as some data. Yeah, this is the structure, and together with some properties. And we have seen some examples also. Yeah, for example, category of sets, category of groups, abelian groups, and all the algebraic ones. Then category of topological spaces, metric spaces with appropriate morphisms. Here there was an exercise that Lipschitz continuous maps. Yeah, the composition of two Lipschitz continuous maps is again Lipschitz continuous. Yeah, that's an exercise in analysis. And we saw one interesting example where objects are just positive integers and home sets are matrices, R cross R matrices. And then we saw that if you take a single object small category, then it is nothing but a monoid, because there is one specific morphism called the identity morphism. The composition becomes multiplication, and that's all you need. Okay, and we ended with the question as to how can you think of a set, a single set, as a category. Does anybody have an answer?
We can take a small category
Huh?
of two objects.
Two objects, okay.
And the home set of from one object to the another different object, that will be a set.
That will be a set, okay. But we want like more categorical properties, so I mean that's fine, I guess. Like you are recovering that as a home set between two objects, but we want something more, like a more prevalent category theoretic construction.
And suppose we have take two elements A, B,
Uh-huh.
capital A, given set.
Uh-huh.
Then define morphism of A, B equal to function from singleton A to singleton B. Unit
Functions from singleton A to singleton B.
A goes to B.
What's the meaning of functions from singleton A? I mean, that will be just one function.
That one function. So my morphism, a collection of morphism from A to B is only one function.
So it's basically an ordered pair, A, B.
Ordered pair. But we want just single set. So how is it giving us what we need?
The question is the same. Think about a singleton set as a category. So we have
Singleton set as a category. Okay.
we have defined a
So you are basically saying home singleton comma A is is a set A. But I would still say that this is an external piece of data. Yeah, you are getting a home set as a set in both those solutions. But if you want that information embedded inside the objects themselves, I think you are trying to generalize this idea of a monoid. Yeah, that's what both of you were doing. Any other ways?
Objects are all the elements of the set and
Only identity morphisms. Okay. So this is called a discrete category. So let me write that example. A category is C is discrete if only morphisms are identities. So then using this definition, I can say that a small discrete category is a set. Yeah, I mean, that's all. You don't have anything apart from what is absolutely necessary. Yeah, identities you can't get rid of. Every object must have identity, and you just have that bare minimum. Okay, so this is what this condition is. You can obviously have large discrete categories. They are not sets, but they are proper classes. Then say that a category C is a pre-order if home C AB is a singleton for any A and B in objects of C. Okay, so this is a pre-order. In particular, when A is equal to B, so home CAA is a singleton. What can that singleton be? It has to be the identity morphism. Yeah, then there is is at most a singleton. I mean, is a singleton or empty. So home CAA must be singleton because identity is always present, but otherwise we do not have any other restrictions, right? So the other restrictions are, so if, let's try to analyze this situation, okay? So yeah, first thing, if home C AB is non-empty and home C BC is non-empty, then what can you say about home C AC? It's non-empty because the composition, don't say transitivity yet, yeah, this is also non-empty. It is basically transitivity, yeah. So when you interpret that home CAB is non-empty, you say A is less equal B, yeah. So rewriting home C AB non-empty as A less equal B, we get reflexivity and transitivity. Why reflexivity? Because home CAA is non-empty, identity morphisms are present, and the property that I wrote above, it says that it's transitive. So reflexive and transitive relations on not necessarily sets. Yeah, I mean, it can be a small preorder or it can be a large preorder, but this is called a preorder. Now, in a preorder, however, there is one condition missing from the usual thing. This is an order relation. So usually we think about partial orders. Yeah, so what is the difference between a preorder and a partial order?
There's no
Antisymmetry. So it can happen that there is a morphism from A to B and there is a morphism from B to A. So we have to quotient out by such things. Yeah, so these are isomorphic objects, okay, and we have to quotient out by such objects, and then we'll get a poset or a partial order. Yeah, poset is an acronym for partially ordered set, but it doesn't have to be a set. Yeah, it can be anything. This is an important thing about foundations, like the standard foundations, namely set theory, that you don't really need the concept of a set to talk about functions. Yeah, every set mapping to its cardinality. Now that's not a set function. Then, so the concept of a function and the concept of a relation is more fundamental than the concept of a set. Right? So therefore, a pre-order is just a pre-order. Order relation is more fundamental than it being a set, like there being an underlying set. So it can be a pre-order which is small or large. It can be a partial order which is small or large. And now that we have started talking about an isomorphism, like quotienting out by isomorphism, so let me define what an isomorphism is. A morphism f from A to B in a category C is said to be an isomorphism if, yeah, tell me some ideas. If there exists a G, you can't say, I mean, normal, our isomorphism is, oh, it should be injective, it should be surjective, like bijective maps which are structure preserving, but there is no bijection concept here. There is no set. There is no function. Yeah, we are just talking about a morphism. If there is some G from B to A such that
f of g equals g of f equals
no, f of g doesn't equal sat.
g of f is the identity of g.
Correct. So gf is equal to 1a and fg is equal to 1b. So it must have a two-sided inverse. Yeah. So that's an isomorphism. Now I'm going to go back a bit and I will show you this thing again. Now look at example 6 again. And in that example 6, we said that morphisms of C, we are talking about a small single object category. Suppose I put the condition that every single morphism is an isomorphism. What will I get? A group. Okay. So a group is a small one object category in which every morphism is an isomorphism. More generally, I'm going to give you a ninth example. A groupoid is a category in which every morphism is an isomorphism. I'm not going to write isomorphism always. Yeah, I will just write an iso. Every morphism is an isomorphism. Okay, so basically, you can go from, there is also a notion of connected groupoid. Connected groupoid means home is non-empty for any pair of objects. Yeah, a groupoid is connected. I'm using word G is connected if GAB is non-empty for all AB in objects of G. So basically, every single object is essentially the same, like any two objects are isomorphic to each other, but still they are different. Yeah, being isomorphic doesn't mean they are equal. In fact, equality is not the right notion in category theory at all. Yeah, everything has to be up to isomorphism, but here there are many copies of this. Okay, in particular, a
So a group can be thought as a groupoid, but groupoid may not be.
yes, a group can be thought of as a groupoid. I was going to write that. Yeah, a single object small groupoid is a group. This is actually the definition of a group, if you wish. Yeah, single object small groupoid. But a groupoid can have many objects. Okay, one instance, like this is for those who know the subject. Yeah, this question is for those who know the subject of algebraic topology. Have you heard of the fundamental group of a topological space? Yeah, what do you assign it to? Is it just an arbitrary topological space or something more than that? A base topological space. Okay, so we want to go in that direction now. So we are going to do another set of examples and then we will talk about the fundamental group and fundamental groupoid. Okay, so set star is the category of pointed sets. Pointed set means it is a set comma one element. So obviously everything here is a non-empty set. Yeah, so objects of set star are pairs A comma A where A belongs to A. Capital A is a set, small a is an element, right? So that is this category. And then what are the morphisms? So set star AA comma BB are all functions from A to B such that functions f from A to B such that it preserves the base point. Okay, so this is set star. Pointed sets and pointed functions, they should preserve the point. I mean, normally you can do it with any concrete category. I mean, roughly speaking, I will define a concrete category later on in the course when we study functors. But loosely speaking, a concrete category is one where the objects can be thought of as sets with some extra structure. Okay, so this is set star, and similarly you can, like top is obviously a concrete category because topological spaces are sets with some extra structure. So we can talk about top star. This is the category of pointed topological spaces and maps preserving the base point. Okay, so you can do it with any concrete category. Yeah, we don't need to worry about just sets and topological spaces. Every group, for example, always has a base point. You can always think of it as the identity element. Monoid also has a base point. Right? So now, once we know top star, then we know that fundamental group, every x comma x naught in top star an associated fundamental group. We call it pi 1 x comma x naught. Yeah, because it has to do with what are the elements of this group, if you can tell me. Equivalence classes of loops at x naught. Yeah, but what equivalence classes? Path homotopy equivalence classes. Very good. I am not going to write down the details of that. And what is the group operation? path concatenation, but path concatenation is not an operation on its own. It's only a binary operation up to homotopy equivalence. Yeah, so remember that. Okay, in fact, given x in top, we can associate a fundamental groupoid this is denoted by capital pi 1 of x. Now, what is this groupoid? So, how many objects are there whose objects are pi 1 x x naught, where x naught is an element of x. It is still in bijection with what I said earlier. So, these are our objects. And what are the morphisms? Yes, morphisms are homotopy, yeah, but we also need some operation of composition. So, homotopy classes of paths between base points. So, tell me, when is this fundamental groupoid connected? When the topological space is connected is not the correct answer. Path connected. Yes. When the topological space is path connected, then this fundamental groupoid will be connected. Otherwise, it won't be. Okay, understood this part? If you don't know algebraic topology, I don't expect you to know these things. These are not important, but I have to be comprehensive while I am doing examples. Yeah, I'm just trying to show you that the more fundamental object than fundamental group is the fundamental groupoid. Yeah, because every point, the fundamental group depends on the base point. So for every point you associate a group. Yeah, so therefore this will work out. Well, now that we are on this topic, let me do 11th example, and that is HTPY, the category of homotopy equivalence classes of morphism. So objects are topological spaces and morphisms are homotopy equivalence classes of maps of continuous maps. We will come back to this particular example when we will study concrete categories. Okay. Any questions so far? Okay, so then let's do one more example. It's slightly different. So suppose T is a formal theory. So we are doing an example from logic. Suppose T is a formal theory and phi are the objects. We define a category. We associate a category. Deductions over T of deductions. The objects are formulas and morphisms are Hilbert style deductions What is composition? Composition is concatenation of deductions, and identities are one-line deductions. If you don't know what they are, don't worry. Okay, examples are never going to be important to understand concepts in this course. Yeah? But for those who know this, we are doing it.
So morphisms are deductions up to some reduction, because otherwise you will compose with the identity, then the length of the deduction will increase, so it will not be the same deduction.
Fine, fine. Yeah, I mean, deductions up to t. Yeah, I mean, t is the set of non-logical axioms we are given, and we are doing everything up to that. Let's, fine, correct. Yes, Nupur, you have a question? No. Okay. Well, some other examples that we can do. I mean, we have to get this image of a function being a morphism out of our brain. We already saw one such example where matrices were morphisms, objects were just positive integers. So this is example number 13 now. This is the category rel. Yeah, this is the category of relations. So objects are sets themselves and morphisms are relations. So given a set A, so can you tell me what is rel AB? Subsets of A cross B, very good. If I write this, relations are all A cross B, subsets of A cross B, power set of A cross B. Okay, so relations themselves can be thought of as morphisms because they have a direction, sense of direction, right? A and then B. How do you define compositions? Compositions of relations. Yeah, so if R is a relation from A to B and S is a relation from B to C, then S composed with R is defined to be all those pairs A comma C in A cross C such that there exists some B in B which connects those two, yeah, such that A comma B is in R and B comma C is in S. So that is the composition of relations. What is, I mean, in this sense, what is the identity? Identity relation is, I mean, the diagonal. Identities are diagonals. Yeah? Okay. Yeah, have you seen composition of relations before? Yeah? Okay, so another example of a similar kind, we will call it part.
Identities are nothing but reflexive relations.
The smallest reflexive relation, right? Which is just the diagonal relation, A comma A. So part is the category of partial functions. So objects are sets and morphisms are partial functions. Perhaps you have not seen this concept. So partial functions are relations where, yeah, I mean, partial function is R subset of A cross B such that if A comma B belongs to R and A comma B dash belongs to R, then B is equal to B dash. So to every element, so normally the definition of function is that to every element of the domain there is a unique element of the codomain. So we relax that condition on the domain. Whenever for some element in the domain there is an element associated with it in the codomain, then that is uniquely determined. Yeah, so no existence property but uniqueness property. That's partial functions. Okay, any questions so far? Okay, then I'm going to define a new way of generating new categories. So if C is a category, then define the opposite category C op by declaring objects of C op equal to objects of C and home, and for any pair of objects, for any pair A comma B of objects of C and a morphism F from A to B in C, we take a morphism F op from B to A in C op. So what's happening, we start with a morphism in the original category and we formally invert it, formally reverse it. Yeah, just reverse the direction. This will also turn out to be a category. Yeah, so basically we have to know, suppose we are talking about 1C. Yeah, what is the op of 1C?
It may happen that the setup of morphism from B to A is empty. How to take corresponding morphism?
If it is empty, then the set of morphisms from, I mean B to A, you are saying, set of morphisms from B to A is empty in category C. Then the set of morphisms from A to B in category C op will be empty. We have one-to-one correspondence between morphisms from A to B in C and morphisms from B to A in C op. You simply change the notion of domain and codomain, swap it. So if one set is empty, then so is the other. But the other dual version, yeah, not the same version. So what is 1C op? If C is an object, then what is 1C op? It's just 1C, yeah, because the domain and codomain, they don't change. And if you are taking F op composed with G op, then that is G composed with F op. Yeah, so this is way of formally reversing the directions. This concept is really useful in orders because you simply reverse the orders. Now let's look at one particular example. So let's consider the set of natural numbers with less equal relation. What are the objects of this category? Natural numbers. And what are the morphisms between natural numbers? Less equal. Yeah, so this is a pre-order. Less equal. Yeah, if n is less equal m, then only there exists one morphism. Otherwise, there exists no morphism. So it's either one or nothing. Okay. Now, what is n op? So we are going to say n less equal op m, which means Yeah, what is this? That n op nm is non-empty if and only if m is less equal n in the original category, which is saying that n and m is non-empty. So we are formally inverting everything. So it's the greater than equal to order. Yeah, less equal op is the greater than equal to. So it oftentimes happens, like for example, consider the collection of all posets. The collection of posets is closed under taking opposites, taking the dual category. Do you agree with that? Yeah, because dual of a poset is again a poset. Dual of a linear order is again a linear order. And in general also there could be many classes of categories in which this particular property is true. That if a category lies in that class, then so does the opposite category. So for such categories, actually we can reduce lot of our work via a simple principle, simple yet powerful principle called the duality principle. Okay, so I am going to state it now. Yes.
M less than equal to n, how did you conclude that morphism from n to n?
Sorry, this is wrong. This is m to n. Yeah, I made a mistake while writing this. Thank you. Yes. Okay, so I'm writing down this very simple looking principle, but it's very powerful because it reduces our work in half. Okay. Suppose X is a class of categories closed under duals. Yeah, i.e., if C belongs to X, then C op belongs to X. By the way, when I am talking about dual, then I implicitly assume that all of you know what will be double dual. What is it? Just the original category. Yeah, it's a map whose square is identity. What are such maps called? Not idempotents. Idempotents are maps whose squares are themselves. Yeah, f square is f. Involutions. Yeah, so duality is an involution. Okay. So suppose X is a class of categories closed under duals. If P is a categorical property true for all categories in X, then so is P op. The property obtained by reversing all arrows and compositions. So what I am saying that if one property is true for a class of categories closed under duals, then the opposite property is also true. Now there are some natural questions here. Let's see if you can ask them. Do you understand this statement? Exactly. We have not defined a categorical property. Yeah. So that is something we need to do now. I mean, I haven't given you any examples, but duality principle is nevertheless valid. Okay, so let us look at an example of a categorical property. Okay, so one example. Say that an object T of a category C is a terminal object if home C AT is a singleton for each object A of C. Okay, so we are defining a terminal object. So there should be only one morphism to T from any object, including T itself.
That has to be unique in any category. T to T always unique.
T to T is, there will exist one morphism at least, which is identity. But in general, there could be many morphisms. So we are saying that identity is the only morphism from T to T. But that is just the tip of the iceberg. Yeah, I mean, we are saying that home AT, if any morphism, there is a unique morphism from A to T for any T, any A. So can you give me examples? Let me go back to slide number 5. Singleton sets in the category of term, yeah, this category of sets. Because how many functions can you define from a set to a singleton? A single function, yeah, because every element has to be mapped to that element. Okay, let's just be extra careful here. What happens if your domain happens to be the empty set? Empty function. Yeah, because what is a function? A function is a triple. Domain, codomain, and the graph of the function, which is a subset of domain cross codomain. Now, if the domain is empty, codomain is singleton, then the cross product of them is empty. So what can be a subset of empty set? Just the empty set. So therefore, it is also true that there is a unique function from empty to a singleton, the empty function. Okay, so always think about these corner examples, extreme examples. So I'm going to write it this using this. So a singleton, I mean, it doesn't matter what that singleton is, yeah. I'm just denoting it by star, but any singleton is a terminal object. Okay. What about groups? The category of groups. Identity what? Identity element. No, identity element, identity morphisms, they are not correct answers. What are the morphisms? Group homomorphism. So we need a group, trivial group, not identity element, trivial group. Think about where you are. Yeah, that's, so trivial group. Trivial group means group containing only one element, namely the identity element. So that is a terminal element, terminal object. Abelian groups? Trivial group, yeah. Are vector spaces one-dimensional? One-dimensional R vector space. Is that unique? Like, is home RR singleton? Singleton zero vector space, trivial vector space. Yeah, you can't say that R is not itself a terminal object. That's not correct. What about category of rings, unital rings? Does there exist a terminal object? Zero ring, I mean, it depends on our choice. Yeah, most likely unital rings, we ask them to be non-trivial. Yeah, 0 and 1 are different. So in that case, there is no terminal. If you allow 0 to be equal to 1, then it can exist. Okay, so I will say there doesn't exist a terminal object. Category of monoids and monoid homomorphisms, again trivial monoid. Yeah, singleton, just identity. Semigroups, again don't say identity. Trivial group, semigroup homomorphisms. Yeah, remember that. If you say singleton semigroup, then can you make sure that there is a semigroup homomorphism from any other semigroup to itself? Yeah? Let everybody be sure. You are saying no? Okay, homework. Try to figure that out. Yeah, then modules, it's the same thing. Yeah, trivial module. Yeah, so I'm not. Topological spaces. Empty space is not terminal point. Singleton space. With what? I mean, do I need to describe the topology on singleton space? Is discrete and indiscrete different on a singleton? No. It's unique. Yeah, so singleton space, just that. Metric spaces. Singleton. I want everybody to verify all these things, okay? Mat R. Does there exist an object which is terminal? I did not include 0. Objects are positive integers. There's no terminal object. Good. A monoid, thought of as a category, is there a terminal object? Depends on the monoid. There exists a terminal object if and only if the monoid is trivial. Yeah, otherwise not. Okay, good. Discrete category. Does there exist a terminal object? If and only if the set or the discrete category is single object category. Yeah. Then preorders. What is a terminal object in a preorder? No, not least element. It's maximum element. Yeah, it's a maximum element over here. Yeah, what's a maximum element? That everything is less equal that. If it exists. Yeah, I mean, I'm not saying that maximal elements exist. I mean, you can see that in these examples, terminal object may or may not exist. Yeah, so even here, yeah, preorder will have a maximal element if and only if, I mean, not if and only if, I mean, if it has a maximal element, then it will have a terminal object, otherwise it won't. Okay. A groupoid. No, directly no. See, first of all, remember, if terminal exists, then the category is connected. Yeah, category is connected means the underlying graph of it is connected. You can go from one object to another object via a zigzag of morphisms. You can go along morphisms or opposite ways of morphisms. So therefore, terminal exists means this is the star. Yeah, everything connects to this. So therefore, the category is connected. So if the groupoid is not connected, then there is no question at all. But if the groupoid is connected, then also a terminal object will exist if and only if the home sets are singleton and there is only one object. Or, okay, yeah, home sets are singleton, that's all. Trivial thing. Yeah, that's okay. Yeah, so terminal exists if and only if all home sets are singleton. Set star. Does there exist singleton set with what point? There is only one point, right? So it always exists. So that is singleton star, comma star. Okay. Top star, same thing. Yeah, I'm not doing that. Then, well, let's not go into these awkward things. Category of relations. Do it as homework. Yeah, figure out, tell me next time whether it has a terminal object or not. Okay. And if C has a terminal object, what will it be in the dual category? Initial object. Very good. So you know the definition. So now I will define an initial object using a different color. So initial object, if home C IA, I mean this is I, notation is I, is a singleton for each object A of C. It's the dual property. So existence of a terminal object is a property of categories. It's a categorical property. So if, now look at the duality principle again. If a class of categories is closed under duals and every single category has a terminal object, then every single category also has an initial object. Yeah, so that's what the duality principle does. It gives you the dual property for free. Now I'm going to use this blue color and we are going to figure out initial objects in different categories. Okay, so in the category of sets, what is an initial object? Empty set. Okay. Category of groups, trivial group. Okay. Abelian group, same. May be same, may not be same. If they coincide, then that is called a zero object. Okay, so we will write that. So category of sets doesn't have a zero object. You can see that. Empty set and singleton are obviously different, not isomorphic. Then trivial groups, so category of groups has a zero object. Category of abelian groups has a zero object. Then category of vector spaces has a zero object. Category of unital rings, does that have an initial object? Z. Why suddenly Z? Right? Everybody should think about it. That 0 should go to 0 under a ring homomorphism. And where can 1 go? 1 has to go to 1. Yeah, and then that will be uniquely determined. If it is a unital ring with 0 not equal to 1, then that morphism is uniquely determined, because what is an arbitrary integer? N, if n is positive, it is 1 plus 1 plus 1. So because it already preserves addition, so image of n is automatically determined. Yeah, f of n is equal to n times f of 1. Right, so that's determined. So z is actually the initial object in this. Modules, it's the same again. Topological spaces, does there exist an initial object in this category? Empty space. Okay, matrix spaces and matrices. Empty space, fine. Provided, I mean, we have to think about whether there is any condition. No, it's Lipschitz continuity is fine with that. Okay, then a single monoid, let's leave that. Discrete category, leave that. Yeah, it's the same answers. When does a pre-order have an initial object? It's a minimum element if exists, and set star, singleton again. Yeah, so this is also a 0 object. Okay, then let's leave these things. Relations I will give you as a homework problem and part, and the dual of initial object is obviously the terminal object. So let me write that a 0 object, an object 0 is called a 0 object if it is both initial and terminal. I mean, here I am already giving you the notation. 0 is the notation used for 0 objects. So in any pointed category, usually the single point is a 0 object. Yeah, so groups are pointed automatically. Now, one thing that we need to observe, let me go back to this slide. So, how many terminal objects are there in the category of sets? Is it unique? There are so many. Yeah, any singleton would work as a terminal object. So, basically the idea is that the existence doesn't guarantee uniqueness, but we never need uniqueness. We need uniqueness up to isomorphism. So let's go to that slide and let us say if T1 and T2 are terminal objects in C, then can you conclude something about T1 and T2? They are isomorphic. How do you conclude that? Then home T1 T2 is singleton. Okay, then C T1 T2, C T2 T1 are singletons. Let me write that. Yeah, so T1 to T2, let's say there is F, and T2 to T1 there is G. And we know that there is one T1, the identity morphism, and there is one T2, the identity morphism over here. And these are the only maps possible between these two objects. So therefore, G composed with F has to be a morphism from T1 to T1, but there is only one possible, namely identity. So therefore, G composed with F is equal to 1 T1. We are forced. And F composed with G is also 1 sub T2. So therefore, F and G are inverses of each other. And they are both isomorphisms. So basically, the objects are isomorphic. So terminal object may not be unique, but it is unique up to isomorphism. Initial objects also need not be unique, but they are unique up to isomorphism. Okay. Now there is one thing I want to show you. Yeah. We want to write this in the form of a diagram. We always, these are special cases of something more general that will come later. The categorical properties that we always desire are called limits and co-limits. And this is a simple thing about like terminal objects are limits and initial objects are called co-limits. Let me go back to a particular example. So this is groups, abelian groups, vector spaces, rings, monoids, semigroups, etc. So associated to each one of them, there is some signature. Yeah, for example, for groups, we saw yesterday that it's a binary operation, then a unary operation of inverse, and a constant which is nullary operation. Then abelian groups also, there is something. Same thing, MIE. For vector spaces, there are scalar multiples, scalar multiplication maps, the unary symbols. Then monoid semigroups, modules. Then you can also add to this list, the categories of posets, partially ordered sets, and monotone maps between them. Then pre-ordered sets and monotone maps between them. Then lattices and monotone and lattice homomorphisms between them. Boolean algebras and Boolean algebra homomorphisms between them. So all of these are algebraic examples of some kind. And I have combined them into a single example too. For a reason, because we can write them, if sigma is any language or signature, then all of them can be written as sigma structures or models of certain theories, like they satisfy some properties. So sigma structures and sigma structure homomorphisms, they will also form a category. Yeah, sigma structure just means like if your language or signature consists of one binary function symbol, then you are taking a set, non-empty set or just a set with a binary function defined on it. Now, homomorphism means it should just preserve that. Similarly, you can do something with relations. So those who are interested in logic, they can understand that sigma structures and sigma structure homomorphisms, that's an important category to understand. And similarly, if you want some properties present, then you write down those properties as axioms, and those axioms will form a theory. And then the category, a subcategory of this, which we call category of models of a theory, that will also be a category. These are some more examples, and they encompass lots of these examples under one umbrella. Any questions about this? Okay, then now finally we haven't finished with the examples of categories yet. So let me write one more example, and that is this. Cat. The objects are small categories. Small categories means the collection of morphisms is a small set, and morphisms are functors between them. Okay, so this is a new term, functor. Now try to recall what Russell's paradox was. Russell's paradox said that the collection of all sets is not a set. But here we are doing that. Yeah, the categories themselves could be objects. Yeah, here we are taking a restriction that these are all small categories, but they themselves could be objects, and then there are appropriate morphisms between categories which make them into a category. This will be a locally small category, and there is also another category that we will consider here, which is objects are locally small categories. And morphisms are functors. Like many books, reference books, they will call it as a quasi-category, but we don't need to worry about that.
So this category cannot be a class, right? We need to identify something about that.
It can be a class. I mean, it will be a class.
I mean, because it contains classes and
The problem is, like, usually in practice people want to work with locally small categories, and if you take one locally small category and another locally small category and take all functors between them, then that's not a set. So it's not locally small, but it's still a category. You can do the same things because in a category we always work with.
it contains a lot of classes, so should make it some like.
So that's why I said, if you are worried about the foundational issues, then you should start with a universe of sets, set theories. Yeah. So, for example, von Neumann universe like V0, V1, V2, where the notion of a class and set are relative, but in general you shouldn't worry about that. I'm just giving you two notations, and the point of talking about these two examples is that our next point of study is going to be functors. Yeah, functors are the natural morphisms between categories, and what should they preserve? If I go back to the definition, then they should take objects to objects. So there should be two categories. They will take objects to objects. Then they should take morphisms to morphisms. They should preserve domain. They should preserve composition, and they should preserve identities. These properties are irrelevant. Yeah, properties are never preserved by structure preserving homomorphisms. So it should just take objects to objects, morphisms to morphisms, identity to identity, and composition to composition. So that's your definition of a functor, and we'll begin with that next time.